Hello everyone. So today we are going to start our AS level chemistry class chapter number 5 is the states of matter. Okay, and I am going directly into the contents of the book. So state the basic assumptions of the kinetic theory as applied to an ideal gas. Okay, so before going into further details, we have to know, we already know about the basic theories of matter, like the movement of particles in solid, in the liquid, in the gas. Okay, here, so in the solid, gases, liquids and solids, we know about them, but still I would tell you, if you do forget, please read them from the book. Now let's go to the gaseous states. Okay, so first of all, look, you know that in a gas sample, the gas molecules move, there is about no intermolecular force of attraction between the gas molecules. Okay, now tell me, why do you think that inside a gas sample the molecules will move quite freely? Tell me why. The molecules will move at high random speeds. Okay, so tell me, why is this? This is because it is assumed that between the gas particles there are no intermolecular force of attraction, or if it does exist, then it exists to a very small amount or very negligible amount. Okay, so the first thing is that there are no intermolecular force of attraction or repulsion between the gas molecules. Okay, so this is the this is what we imagine that that this has to happen in a gas sample. So a gas sample in which there is actually no or negligible attractive force between the particles, we call that gas sample an ideal gas. Okay, but in reality, anything that contains electron must attract other particles by van der Waals force. So in reality, ideal gas is almost non-existing. Okay. Okay. So the gas molecules move rapidly and randomly. This is one condition. The distance between the molecules is much greater than the diameter. This means, for example, okay, so this is the diameter of this molecule. Okay, and this is the diameter of this molecule, and this is the distance between them. The distance between them has to be greater than the sum of their diameter. Okay, if here the distance is d and here the diameters are d1, okay, and the diameter is here d2, so it should be that d1 plus d2 must be much less than d. Okay, so all collisions between the particles are perfectly elastic. This means that no kinetic energy is lost in collisions. Okay, so we will come to this later on. All right, now you must know that these themes are followed. A gas sample that follows these themes are called the ideal gas. Okay, ideal gas. Now the most important theme of all of them is this one, because to satisfy this condition, if this condition is satisfied, then all other these conditions are also satisfied. Okay, so there is no intermolecular force of attraction between the gas particles is the most important point to be noted. Now let's go into the explanation of this. Okay, for example number 1, firstly, the gas molecules move rapidly and randomly. Okay, so if the gas molecules had attractive force between them, then movement of one gas molecule would be affected by another gas molecule. For example, this gas molecule is trying to move in this direction, but this gas molecule is trying to move in that direction. Okay, So their movement would be slowed down. Okay, their movement will be slowed down because there are attractive forces between the particles. So their speed would not be high, and so they cannot move randomly. Okay, randomly means according to their own wish. So if the gas molecules has to move randomly, then there must be no intermolecular force or no attractive force of no intermolecular force, that means the force of attraction or repulsion between the particles. Okay. Now secondly, the distance between the gas molecules is much greater than the diameter of the molecules. Okay. So the molecules, this seems that the molecules are very much far apart. All right. So this means that if the molecules are far apart, then there is a very minimum chance of formation of attractive force or formation of repulsive force between the molecules when they are far apart. Okay? So that's why the distance between the particles must be greater. All collisions are perfectly elastic. Okay, so all collisions are perfectly elastic. Now a collision is elastic. You know, the Newton's third law, that every action has an opposite and equal reaction. Okay, for example, two particles are undergoing collision with each other. Okay, so two particles here are colliding. So this particle applies a force on that particle, the force F, and in return this particle applies a force on that particle, the force F. So these two forces are equal. Okay, and the collision is elastic, that means the momentum is conserved when there are no other forces rather than the action force and the reaction force. If no other forces are present other than these two forces, then there is a possibility that the type of collision between the two particles may be elastic. And what happens during an elastic collision? The total kinetic energy of the particles before collision and the total kinetic energy of the particles after collision, they become equal. Okay? For example, before collision, this particle is moving with kinetic energy of 10 joule, and this particle is moving with the kinetic energy of 20 joule. So what is the total kinetic energy? 30 joule. Okay? And after collision, when the particles are moving away from each other, suppose the first particle is moving with a speed of say about 11 joule, and the second particle is moving with a kinetic energy of 19 joule. So still it remains total 30. If this happens, that the total kinetic energy before and after they are equal, so we call it a elastic collision. Okay. Now the first condition is that there should be no other forces between the two particles rather than that force of the action or the reaction force. So if any intermolecular force, that means the force of attraction or repulsion, is present, then that would be a third force beside the force of action and reaction. Okay? So in that case, the collision would not be elastic. Okay? So that's why if the collision has to be elastic, then again there should be no force of attraction or repulsion between the molecules. All right? Okay. So that's why all the conditions, all the conditions that are mentioned over here, the main point is that there should be no attractive force between the particles. Point number 3. Okay. So a gas that follows these rules are called an ideal gas. Okay. But in reality, no gas is ideal, because the particles, there is always some intermolecular force that is acting between the particles. So it should be like ideal gas is just an assumption. Okay, but we can try to convert a real gas into ideal gas by minimizing the force of attraction or repulsion between the particles. How? Okay. So number one, let's heat the gas. Heat the gas sample. Okay. Now, if you heat the gas, then the particles of the gas is going to gain they're going to gain some kinetic energy and move very fast. Okay. So, when they are moving very fast, there is a very small possibility of attractive force of the formation of attractive force or the formation of repulsive force between the particles because they are moving very fast. Okay. So, when you heat the gas or when you increase the temperature of a gas, then it is possible that the gas might act as an ideal gas. And secondly, when you make the pressure of the gas low or increase the volume of the gas, pressure low, or number 3, increase volume of gas. Okay. So, when you are making the pressure of the gas low, which is equivalent to increasing the volume, they all means the same thing. So, when you are making the pressure low or increasing the volume, this means you are increasing the volume, you are increasing, this was the container, now you are increasing the volume of the container, which means that in the first container the particles were close together, but in the second container the particles are now far apart, isn't it? So, that means that distance between the particles has increased, and therefore, the attractive force or the repulsive force between the particles would be minimized, and therefore, the gas would start to act like an ideal gas. So, at high temperature or heated state and at low pressure or increased volume, a real gas would start to act like an ideal gas. Okay. Okay. Now, let us go to the mathematics of ideal gas. Okay. Ideal gas follows certain laws. Now, one of them being what we call is the Boyles Law. That means, okay, so let us see that which factors affect the different dimensions of gas, like what are they? Pressure, is the size. Okay, so pressure, volume, temperature, and number of moles of gas. Okay. So, let us see the relation between the different factors. Okay. Firstly, let us relate each and everything with pressure. Okay. So, pressure will be inversely proportional to the volume. It is so simple. Like if you increase the volume of the gas, then the pressure would be reduced, or if you increase the pressure of the gas, then volume would be reduced, isn't it? Just imagine that you are taking a syringe, and this is the piston, and you are pressing on the piston. That means you are applying a high pressure on the piston. So, and this is the amount volume of gas in the piston. So, if you press it, then piston is going to come down, and the space inside the syringe would be reduced. That means the volume would be reduced. So, if you increase the pressure, then the volume is going to get reduced. Okay. So, that is why pressure is inversely proportional to the volume. Okay. Now, let us go to our next factor, pressure versus temperature. Now, tell me, if you increase the temperature, for example, let me draw a simple diagram. Suppose this is a wall, okay, and a particle is hitting on the wall with lower speed. Okay. When the particle is hitting with a lower speed, it will create a pressure on the wall which is lower. Now, imagine the particle is hitting the wall with a very, very high speed, then it will bounce off with a very high speed and will create a high pressure. Okay. So, the pressure created by a particle will also depend on the speed of the particle. Okay. Now, so how can we increase the speed of a particle? I have mentioned few moments ago that if you increase the temperature of the gas, then that's going to change the kinetic energy of the gas particles, and that means the speed of movement of the gas particles. That means if you increase the temperature, then the gas particles is going to move faster. Okay, so faster, that means with a greater speed. So they are going to hit the wall of the container with a greater speed, isn't it? So the pressure will increase. So pressure will be directly proportional to the temperature. Okay. Okay. So we have got two relations, but we have got one more relation to go. Now imagine. Okay, please note these two things down. I'm going to rub it. Okay. So now, okay, so here the illustration is given: low temperature, high temperature. All right. Okay. So now imagine that you are given a box, actually two boxes of same size. Okay. So one box contain 1, 2, 3, 4, 5, 6, 7, for example 7 moles of gas particles, and the second box contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16, 17, 18, 19, 20, 21. Okay, so a second box contains 21 moles of gas particles. Now tell me, where or in which box there will be greater number of collisions? Is it here? No, it is here, because there are more number of moles of gas particles, so there will be more pressure. More collisions, so there will be more pressure. So what can we say? We can say is that pressure will also be proportional to number of moles of gas. Okay. Now let's combine all these things together. So we can say that pressure is proportional to 1 by volume, and is directly proportional to temperature, and is directly proportional to number of moles. All right. Okay. So let's bring a constant. So pressure will be equal to a constant which we are calling it as R. R means the universal gas constant, into T n by V. Now let's bring the V to this side. So it would now be PV is equal to R T n, or let's rearrange the equation. PV equals to N R T. Okay. So this equation, that PV equals to nRT, is known as the equation for ideal gas. Okay. So this equation is very important. The derivation is not that much required, but you need to know some more derivations from here, this equation. Like for example, you are asked to find a relation between volume and temperature. Okay, so volume and temperature, let's write the equation first. So PV equals to N, then R, then T. Okay, so since you have to find a relation between volume and temperature, imagine all other things are constants. So rub them and then put, okay, you also have to rub the equal sign. Okay, and now put a proportional sign between V and T. That means volume will be directly proportional to the temperature. Okay, so now find a relation between, for example, PV against T, okay, or PV against T. So what would happen? So PV against T, PV versus T, okay. So what you have to do, write the equation first. So PV equals to N R T. So PV against T. So rub all other things. So PV against T. Now put a proportional sign between PV and T. So PV against T has to be also, they are also directly proportional. Okay. Now find a relation between PV against V, PV versus V. Okay. Okay, so PV versus V. Okay, please copy this. I'm going to rub it. Okay, so we know that PV equals to nRT. So PV against V. So PV is present. You know that. P. We know that P is inversely proportional to V. Okay. Now, if we remove the proportional sign, okay, not in this way. So PV against V, so only P and V should remain and all other things should go. Okay, so all other things should go. Now PV against V. Okay, so only, so we can say, sorry, so we can say, that PV, so if all other things are removed, then PV is proportional to K. That means P and V is a constant. Okay, since all other things are removed, the formula said that relation said PV against V. So P and V are all the things that should remain. So that's what remains over here. So the equation came like P is proportional to K, or PV would be equal to K. That means P and V against V. That means PV is always constant no matter how V are changed or no matter how P are changed. P into V will remain constant. Okay. Okay, so in this way we can find a lot many relations as we want to. Okay. Now you have to learn drawing graphs. Like let's learn some basic graphs. Okay. This is the graph for inverse proportion, which will neither touch the x-axis nor touch the y-axis. Okay, and this is the graph for direct proportionality. Okay, so this is the second one. Please rub it. So this is inversely proportional, this is directly proportional, and now this graph means it's a constant. All right. Okay, so if I tell you draw a graph for an ideal gas, draw a graph of P versus 1 by V. Okay, so P versus 1 by V is the graph that you have to draw. So take 1 by V as x. Okay, so we know P is inversely proportional to V. Now 1 by V we have considered x, So P should be proportional to X, isn't it? So that's why P against X is a direct proportion graph, right? Copy it. So, okay. So if the graph is drawn as P against X, where X is equals to 1 by V, since it is directly proportional, so it will be a straight line through the origin. Okay. But however, if the graph says that draw a graph of P against V, okay, so it's a P against V. So it says P against V, but the relation is P is proportional to 1 by V. So we have to keep here V, not 1 by V. Okay. So P is inversely proportional to V. So if we draw a graph of P against V, it will be an inverse proportion graph. That means like this. Okay. But in the last graph, we had to keep 1 by V, not only V. Okay. Okay, this is how it works. Okay. In this way, you can draw as many graphs as you can want. Like we have also seen the graph of PV against T, which was like this. So if we draw a graph of PV against T, the graph would still be a straight line through the origin. All right. Okay. Okay, so we were studying the graphs of P, V, T and N, various types of graph. Like now if you are asked to draw the graph of PV versus V, okay. So PV versus V, so all that involves is P and V. So you know that PV equals to nRT. So if P and V only has to be involved, then cut off n, r and t, then all these things become constant. So we get PV equal to constant. Okay. So if we draw the graph of PV against V or PV against P, then whatever it is, the graph would be constant for ideal gases. Okay. And the graph would look like this. Suppose this is the axis of PV and this is the axis of V or P, the graph would look like this. Okay, it's a constant. Now for various cases we will obtain various types of graph. Okay. Okay, now we will deal with cases that when two or more gas containers are combined together, or the temperature or the pressure state of a single container is changed. Okay. So now first of all let me tell you something. When number of moles, when number of moles, or when a system is closed, for a closed system. Closed system means no further gases can enter into the system. Okay. There is no further entry of gas into the system, or no amount of gas is going out of the system. Okay. So this is what we mean by a closed system. And for a closed system, the formula will be PV by T. Okay. PV by T before or initially will be equal to PV by T after. Okay. So PV by T initially must be equal to PV by T after. Okay. And if any quantity remains constant, you can cancel that quantity from the equation. Like in one of the case, if T remains constant, then cancel the T. Okay. If for example P remains constant, then cancel P. Okay, just like this. Or if V remains constant, then cancel V. So simple. Okay. Now let's apply this formula for closed system. Okay. So for a closed system, let me give an example. Okay, this is a container, the black container. This is a red container, and inside this, and inside the black container, let its volume is V1, the pressure inside the gas is P1, all right, and the temperature of this container is T1, okay, and inside this red container, the volume of the gas is V2, the pressure is P2, and temperature of the gas is T2, okay. Now what happens is that the theory says that these two containers are now combined together. Okay, so these two containers are now combined together like this. So what happens is that the gas within them now mixes. Okay, so there is a mixing of gas within the container. Let me show you in an imaginative way. Okay, so okay, now what happens over here is okay, so now it's a mixture. Okay, so let the pressure, the state of pressure, the state of temperature, and the state of volume here let the pressure is P. Okay, so much thick. Let the pressure here is P. Okay, so the if since these two containers are solid containers, so the volume of this container will remain V1 and volume of this container will remain V2. So the total volume would be V1 plus V2. Okay, and let the temperature is unknown to us, and this temperature is T. So this is the case before, okay, and this is the case after. Okay, so this is the case before and this is the case after. Okay, now what's going on is that so what we have learned, that PV by T before, total PV by T before must be equal to total PV by T after. Okay, here for example V1 plus V2 together we are telling it as V. Okay, so total PV by T before, so in case of this black sphere we have P1 V1 by T1, and in case of the red container it's P2 V2 divided by T2. Okay, and this must be equal to P V divided by T, where this is after. Okay, so the total PV by T before must be equal to total PV by T after. Okay, so that is the case. So in case of closed system, that when no gas can enter or leave the system, the formula would be this, the total PV by T initially or before must be equal to total PV by T after. All right. Okay. Now let's go for an, one more thing. Okay, so this is a container which contains a specific volume of gas. Okay, and this gas is heated. Okay, this gas is heated. So if this is a solid sphere, for example, okay, so before heating, okay, before heating the pressure, before heating the gas, let the pressure inside the container was P1 and its temperature was T1 and its volume is V. Okay, this is a solid sphere, and after heating its pressure is P2, then temperature is T2 and volume remains V. We here consider that volume remains constant because this is a solid sphere. So PV by T before, that means P1, okay, so V remains constant, so we can cancel out V. Okay, so P1 by T1 is equal to PV by T after, and since V is constant, so we are cancelling V. So just P1 by T1 equals to P2 by T2 is the formula in this case. All right. Okay. So now there would be various types of formula for various cases. Now, if the system is a closed system, then what would be our formula? The formula would remain the same, just extra n will be included, like PV by NT is equal to PV by NT. Okay, so PV by NT and PV by NT. PV by NT initially is equal to PV by NT finally, or PV by NT before must be equal to PV by NT after, and this is the formula for what? This is the formula for the closed system. Okay, sorry, for the open system, where gases can leave the system or gases can enter the system. Okay. Again, if any quantity remains constant, then we can cancel it out from our equation. Okay, now let's see, for example, this is a red container. Okay, and imagine that here is a space. Here is a small space like here. Okay, so through which gases can enter or leave. All right. Okay, now for example, so this is an open system. So here before, the pressure of the gas was P, volume of the container is V, number of mole was N1, okay, and temperature was T. And after some gas entered the system, what happens? The pressure becomes P2, the volume is V, number of moles become N2, and temperature remains T. That means here the volume and the temperature remains constant. Okay, so from the equation we can cancel out the volume and the temperature. They can be cancelled out. Okay, so we can say that our formula would be P1 by N1 must be equal to P2 by N2. Okay, the V and T is cancelled out. Okay, now tell me what would be the formula when air is getting into the balloon or air is going out of the balloon. Okay, so inside a balloon, okay, so inside it the pressure, the volume, all thing changes. Okay, the temperature may remain the same, or the temperature is considered to remain the same. Okay, so let's draw a balloon. Okay, so it's a blue colored balloon. Let me see. So before, this was the size of the balloon, but after some air has leaked out. Okay, some air has leaked out. Okay, now this is the size of balloon. Some air has leaked out, and inside the first balloon let the pressure was P1, volume of the balloon was V1, number of moles was N1, temperature was T, and inside the second balloon, let the pressure is P2, volume of the balloon is V2, number of moles of gas that remains in the balloon is N2, and temperature is T. So, okay, so here the temperature remains constant. So, what would be our formula? PV or P1V1 by N1 must be equal to P2V2 by N2. Okay? From here, we can find the required quantities. Okay, so inside this balloon, number of mole that remains is N1, and inside this balloon, the number of mole that remains is N2. So, how much mole of gas has leaked out? So, leaked out equals to N1 minus N2. Got it? Okay, so this is how we should carry out the calculations. Okay. So, this is our first video of the states of matter chapter, and here we have dealt with the properties of ideal gas, and then the mathematics that will be related to ideal gas, the graphs of the quantities related to ideal gas, and in our next lecture video we will discuss on the liquid state, okay, the liquid state, then solid state, okay, and then the vapor state, and then we will be finishing this entire chapter. Okay, till then we will finishing this chapter by next week, inshallah, or within this week. I would say today is Monday, so we still have till Thursday. So I think by Thursday I will upload another video and have a class. Okay, so I will inform you the class timing. Till then, goodbye.